Now that we know our rotational variables, we need to set them into motion. So as my old physics professor, Dr. Fred Loxam, used to say, he was from the Northeast, we're going to talk about talk. So what we're going to do is describe, I should say, torque. That is a push or pull around an axis of rotation. To talk about torque, you have to identify the axis of rotation. So let's start by applying a torque to something. So here we now have a metal disc that is free to rotate. And to apply a torque, I simply give it a little push on the edge. And when I do that, I increased its angular velocity, I applied an angular acceleration, etc. But first, let's now just focus on the torque. So here we've got the disc, and I just brought in my finger here, and I applied F push, kind of like we talked about on translational kinematics. We applied F push. There's a center to the disc, and it has a radius r. Okay? Let's see. And what I need to start doing is specifying the axis of rotation. So in this case, the disc is pinned at its center. So I'm going to use a little star like that to specify that is the axis of rotation. Since it's an axis, it's really a line. Usually, though, when we have something rotating, we draw it in the plane of the page or the board. So an axis is always coming out. So the star means the axis of rotation is an axis. It's a line coming out of the board. So very important to specify the axis of rotation. So to figure out the torque, to calculate the torque, you actually have to make r a vector from the axis of rotation to the point the force is applied. Is applied. R is a vector, it's not a scalar. So in this case, we would actually draw my R a little bit different. Here I was just trying to label the radius, but now why don't I actually draw the R vector? It's from where the axis of rotation occurs, which is set by how something is set up, right? I could have the axis of rotation here if I had the bearing holding it here, but I have it set where the bearing is mounted at the center, therefore it rotates at the center. Anyway, so it's from the axis of rotation to the point the force is applied when my finger applied it at the top. So there is R. Okay? It's a vector, it starts at the axis, it goes to the force. You got to be able to find the R. The F vector, of course, you're used to thinking of force as a vector. It's from the point you apply it and you go draw it in the direction of the vector. So torque then, T-O-R-Q-U-E, torque, tau is the symbol, tau for torque, and it's that magnitude of that radius vector, it's just r, plain old r, times the magnitude of the force vector times the sine of the angle between them. Okay? Now, the angle between them means add them tail to tail. It means the angle between the two vectors. So in this case, we would draw and say R is up, like that, and F is this way, like that. So the angle from R to F is what? It's theta. But in this case, theta equals minus 90 degrees. If you're doing your angles properly, remember, clockwise is negative. So we had to move 90 degrees, and we moved clockwise 90. So technically, that theta is negative 90 degrees. So in this case, if we plugged in our values, torque in this case would be minus r, the radius of the disk. I'll start calling it rd since it's a specific r, times fp, the force of the push, right, times the sine of the minus 90 in between them. We'll just call it fp. There you go. Okay. So that's how we calculate torque in that case. But we're not quite done, because guess what? Torque is a vector. Seems like a lot of things are vectors in this area of physics, and it's true. Now keep in mind, a lot of problems don't require you to really treat it as a vector. A lot of problems, everything's 90 degrees, everything's one dimension. You don't have to do formal vector notation. But for some problems, it's very important to realize, yes, it is a vector. So torque is a vector. This is how you get its magnitude. It's just the magnitude of the radius vector, the magnitude of the force vector, and the sine of the angle from radius to force. This is the cross product if you're into that sort of thing. But to get the direction, the easy way to get the direction is to say the torque is a vector, the direction equals the direction of the angular velocity it tends to create. Okay? So if you were to look at this problem and say the torque is making this thing go clockwise, that would tell you that if you wanted to draw the torque vector, it would be one into the board. Right? Because clockwise means negative. Or you could apply the right-hand rule. Same way you figured out for omega. This torque is going to tend to make it turn this way. So you take your right hand, you make your fingers go along the direction it wants to turn, and your thumb goes into the board. So there's your torque vector, like that. So that's torque. Torque is what sets your rotational or your object into rotational motion, as we're going to cover next.